Hi, my name is Rohit Pasula and this is my video for Lab 4, Circuits and Capacitors. The objective of the lab is to utilize the conservation of energy principles to predict the behavior of circuits consisting of both capacitors and resistors. We will observe this behavior through an online simulator using multimeters to determine potential difference and current. The fundamental principles demonstrated throughout the lab are Kirchhoff's circuit law, including the node rule and the loop rule. The Ohm's law is also essential towards the experiment. The procedure of the lab includes first predicting the currents I1 and I2 that would be measured by the two ammeters. Afterwards, you would simulate the circuit in the CCK and compare the prediction with the model. Then you would replace one of the ammeters with a voltmeter and compare findings. Finally, you continue to look at potential difference and current at different locations on the circuit and differentiate the findings. Before calculating the current, there are a couple of assumptions that we must make. The resistance from the wires is negligible as well as the resistance from the ammeters. Now regarding the calculations in order to determine the current of the circuit, we know that I1 is equal to I2 due to the node rule. Further, since the resistors are in series, the resistance can be added together to have 147 ohms as total resistance in the circuit. Finally, utilizing Ohm's law, we calculated the current to be 0.02 amps. Now comparing it to the model, our calculations were correct. The expected value was 0.02 amps as well. One thing to note when creating the circuit is that it is important to input the ammeter accurately in the model because it would read negative 0.02 amps if inserted backwards. Replacing an ammeter with a voltmeter gave readings of 3 volts and 0 amps for the current. This is a result of the circuit being open, therefore losing the current but having the same potential difference as the power source. Here is a list of potential differences between different sections during the circuit. As you can see, the sum of the potential differences is 0, as it should in terms of the loop rule. Now here's a complete version of the electric potential versus position graph. The electric potential increases during the path where the batteries are located, but decreases during the path where the resistors are located, ultimately going to 0. Now when an ammeter is added parallel to the 100 ohm resistor, the current increases to 0.06 amps because less current comes into contact with the resistor. Here are the calculated resistance levels for the circuit components and they are incredibly similar to their actual levels. Now in terms of our RC circuit, there are 2 phases. When the battery is connected to the light bulb and capacitor in series, the bulb starts out bright but then slowly dims out. The current essentially decreases from its maximum to 0. This is considered the charging phase as the capacitor is getting polarized. The following phase is when the battery is removed. The bulb again lights up brightly, then decreases in brightness, demonstrating the discharging phase. The current essentially decreases from its maximum to 0 again. This brings us to our data and graph. The inverse of the slope of the graph represents RC, which is the time constant. After recording data from the simulator, the RC was calculated to be 5.974 seconds. The expected RC value was 6 seconds, as is simply the resistance, 30 ohms, multiplied by the capacitance of the resistor, 0.2. Our answer was pretty similar. Now there are some possible sources of error that may have occurred during the course of this experiment. Error should be limited when constructing the models in an online simulator as no measurements are being taken. The main source of error is human error when stopping and starting the stopwatch to record the change in potential difference in the capacitor. So for our reflection questions, what if you're doing this lab in real life and use an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter and how would it have affected the circuits you hooked it up to? Utilizing a real ammeter would decrease the current in the circuits as it will hold some resistance value. Unlike the ideal ammeter in the model circuit that had its resistance negligible, using a real one would have some form of resistance. Now what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Well, the ideal model would predict the capacitor to be charged instantaneously. In reality, however, the circuit components all have some little resistance. Thus, it would take longer than the model to charge the capacitor. So, thank you for listening and have a great day.